Welcome to the fascinating world of Casimir propulsion, where the boundaries of physics are not just theoretical lines, but the very engine blocks of advanced field architecture. In this chapter, we dive into how the AEON-CASIMIR initiative leverages engineered boundaries to create artificial asymmetry in the vacuum, shaping zero-point energy gradients and coupling quantum effects to the curvature of spacetime itself. This approach is not about simply harnessing energy, but about redefining how boundaries can be used to manipulate the very fabric of reality. Let's begin by understanding why boundaries are so crucial in this revolutionary propulsion system. Casimir forces only arise because boundaries exist. Without these engineered boundaries, the quantum vacuum remains perfectly balanced. No directional forces, no propulsion. The AEON-CASIMIR approach is all about breaking this symmetry. By carefully designing boundaries, we can create regions where vacuum fluctuations are no longer isotropic, allowing us to tap into the latent energy of the vacuum and direct it for practical use. This is the foundation of boundary engineering, setting the stage for everything that follows in advanced propulsion physics. AEON-CASIMIR system doesn't just accept the vacuum as it is, it actively reshapes it. By introducing artificial asymmetry, the system manipulates zero-point energy gradients, effectively turning the vacuum into a dynamic, controllable medium. This is achieved through precise boundary engineering, which allows for the coupling of nanoscale quantum effects to the much larger scales of spacetime curvature. In essence, the boundaries become the interface between the quantum world and the macroscopic universe. The heart of this technology is the Casimir effect, a quantum phenomenon that arises between two closely spaced parallel plates. The pressure between these plates is not just a curiosity, it's a powerful force that scales dramatically with the separation distance. In the AEON-CASIMIR framework, this effect is generalized beyond simple parallel plates to include non-parallel, anisotropic, and even curved cavities, all embedded within a lenticular geometry. This flexibility is key to harnessing the Casimir effect for propulsion. Traditional Casimir experiments use two ideal parallel plates, but AEON-CASIMIR takes this much further. By designing cavities that are non-parallel, curved, and anisotropic, the system can tailor the vacuum forces to suit specific engineering needs. This approach allows for the creation of complex field architectures that can direct energy and momentum in ways that simple geometries cannot. The result is a highly adaptable propulsion core, capable of responding to a wide range of operational demands. Cavity walls in AEON-CASIMIR systems are not made from ordinary conductors. Instead, they use advanced metamaterials, engineered substances with properties not found in nature. These materials are anisotropic and frequency selective, meaning they can control electromagnetic fields in highly specific ways. With negative effective permittivity and directional permeability tensors, these boundaries break the standard Casimir symmetry, opening up entirely new possibilities for manipulating vacuum forces. Using metamaterials with unique electromagnetic properties, AEON-CASIMIR cavities achieve boundary conditions that are impossible with conventional materials. For example, the electric and magnetic field components at the wall do not vanish as they would in standard setups. This deliberate breaking of symmetry is what allows the system to generate directional vacuum stress, a critical ingredient for effective propulsion and field manipulation. Vacuum stress in these engineered cavities is not just a simple pressure, it's a local contribution to the stress-energy tensor, the same mathematical object that describes energy and momentum in Einstein's theory of relativity. In curved cavities, the divergence of this tensor is non-zero, meaning that the vacuum stress can be converted into usable thrust or even bias the curvature of spacetime. This is where quantum field theory meets general relativity and where the real magic of AEON-CASIMIR happens. Casimir cavities are curved or arranged in complex geometries. The resulting vacuum stress is no longer uniform. The divergence of the stress-energy tensor becomes non-zero, which means the system can generate net forces or even induce curvature in spacetime. This is a fundamental departure from classical physics, where forces are typically balanced and symmetric. Here, the engineered asymmetry is the key to unlocking new forms of propulsion. AEON-CASIMIR system employs a unique architecture, stacked Casimir cavities arranged radially in a lenticular or lens-shaped geometry. The upper dome contains expansion-bias cavities, the lower dome has compression-bias cavities, and the equatorial ring provides neutral stabilization. This arrangement creates a net spacetime gradient aligned with the thrust axis, allowing for controlled and directed propulsion. The lenticular stack is the physical core of the propulsion system. Within the lenticular stack, different regions serve distinct purposes. The upper dome is biased toward expansion, helping to create a gradient that supports upward thrust. The lower dome, in contrast, is biased toward compression, anchoring the system and balancing forces. The equatorial ring acts as a stabilizer, ensuring that the overall structure remains balanced and effective. This careful orchestration of zones is what enables precise control over the propulsion vector. One of the most remarkable aspects of the AEON-CASIMIR system is its ability to bridge the gap between the nanoscale and the macroscale. Cavity separations are on the order of nanometers, yet their effects are summed coherently to produce macroscopic influences on spacetime. This is achieved through a process called coherence amplification, which ensures that the tiny forces generated at the quantum level add up constructively, resulting in a significant net effect. Total effective pressure generated by the stacked cavities is not just a simple sum, it's amplified by a coherence factor. This factor, enforced by plasma locking mechanisms described in previous chapters, ensures that the quantum effects remain in phase and reinforce each other. The result is a dramatic increase in the overall pressure, making the system far more efficient and powerful than would otherwise be possible. Geometry of each CASIMIR cavity is not fixed. Instead, it can be actively tuned in real time using piezoelectric lattice deformation, plasma pressure loading, and electromagnetic phase biasing. This means the effective separation between cavity walls becomes a function of time, allowing for dynamic control over the CASIMIR effect. Such modulation enables the system to respond to changing conditions and optimize performance on the fly. Making the cavity separation a time-dependent variable, the AEON-CASIMIR system can create dynamic CASIMIR effects without the risk of photon emission instability. This is achieved through precise control of the deformation amplitude and frequency, ensuring that the system remains stable while still benefiting from the enhanced vacuum forces. This level of control is essential for safe and reliable operation in advanced propulsion applications. Modified Einstein equation used in AEON-CASIMIR incorporates the CASIMIR stress as a direct contributor to spacetime curvature. This means that the vacuum stress generated by the engineered cavities doesn't just act as a force, it actually biases the metric of spacetime itself. This is a profound shift from Newtonian thinking, where forces act on objects, to a relativistic view where the very geometry of the universe is shaped by engineered quantum effects. The AEON-CASIMIR framework, CASIMIR stress acts as a metric bias rather than a conventional force. This means that instead of pushing or pulling objects in the usual sense, the system reweights spacetime itself, altering how objects move within it. This subtle but powerful distinction is what allows the technology to remain consistent with both quantum mechanics and general relativity, bridging the gap between the two. Despite its advanced quantum and relativistic underpinnings, the AEON-CASIMIR system is designed to reduce smoothly to classical Newtonian gravity at large scales and low gradients. When the cavities are de-energized, the system's behavior matches that of ordinary matter and vacuum, ensuring compatibility with established physics. This consistency across regimes is a hallmark of robust physical theory and a key strength of the AEON-CASIMIR approach. The Newtonian limit, the effective density that determines gravitational behavior, includes both ordinary matter and vacuum contributions. This means that the AEON-CASIMIR system can modulate gravity by adjusting the balance between these components. When the cavities are active, vacuum contributions become significant. When de-energized, the system returns to classical gravity. This tunability is a powerful tool for advanced propulsion and field manipulation. One of the challenges in manipulating vacuum forces is ensuring system stability. Potential instabilities include vacuum collapse and runaway boundary attraction, both of which could be catastrophic. The AEON-CASIMIR system addresses these risks through plasma-mediated damping, harmonic detuning, and phase staggering of the cavities. These measures ensure that the divergence of the stress-energy tensor remains controlled, preventing unwanted runaway effects. Through careful engineering, the AEON-CASIMIR system achieves a dynamic equilibrium where the time derivative of the divergence of the stress-energy tensor approaches zero. This means the system remains stable over time, with no uncontrolled growth or collapse of vacuum forces. Achieving this balance is critical for safe operation, especially in high-energy or high-curvature environments. Extreme conditions, such as high mass-equivalent loading, local event horizons, may form transiently within the system. However, the AEON-CASIMIR architecture is designed so that the CASIMIR cavities remain external to these horizons, thanks to precise metric shaping. This allows the system to traverse the so-called horizon skirt without entering a singularity, opening up new possibilities for controlled exploration of extreme gravitational environments. Ability to traverse the horizon skirt without entering a singularity is a major breakthrough. By keeping the CASIMIR cavities external to the horizon, the system maintains control and avoids the destructive effects associated with singularities. This capability could have profound implications for future space exploration and our understanding of black holes and other extreme astrophysical objects. Chapter 5 of the AEON-CASIMIR Dossier is not an isolated piece. It integrates seamlessly with the broader propulsion stack. The boundary engineering principles described here enable the thrust generation of Chapter 1, the curvature shaping of Chapter 2, the inertia control of Chapter 3, and the coherent stabilization of Chapter 4. Together, These chapters define a complete, physically grounded engine core for advanced field propulsion. Culmination of boundary engineering is the definition of the physical engine core. This core is not just a collection of parts, but a coherent system that unites quantum, relativistic, and classical physics. By leveraging the unique properties of metamaterial CASIMIR cavities, the engine core becomes the heart of the AEON-CASIMIR propulsion system, capable of unprecedented control over spacetime and motion. Key insight from Chapter 5 is that CASIMIR propulsion is fundamentally boundary-limited, not energy-limited. This means that the performance of the system depends on how well the boundaries are engineered, rather than on the amount of energy available. By focusing on boundary design, the AEON-CASIMIR system achieves efficiencies and capabilities that would be impossible with traditional energy-based approaches. Metamaterials enable the creation of directional vacuum stress, a critical feature for effective propulsion. By controlling the orientation and properties of the cavity walls, the system can direct vacuum forces along specific axes, maximizing thrust and minimizing unwanted side effects. This level of control is only possible with advanced boundary engineering and precise material science. One of the most exciting aspects of the AEON-CASIMIR system is its ability to use nanoscale physics to influence macroscale spacetime. By coherently summing the effects of countless tiny cavities, the system can generate forces and curvatures large enough to move spacecraft or alter gravitational fields. This is a true example of quantum engineering at its most ambitious. The AEON-CASIMIR system is designed to be consistent across quantum, relativistic, and Newtonian regimes. This means that no matter the scale or energy involved, the system's behavior can be predicted and controlled. Such consistency is rare in advanced physics, and it speaks to the robustness of the underlying theory and engineering. Like traditional propulsion systems that push against spacetime, the AEON-CASIMIR craft reweights it. This means that instead of applying a force in the usual sense, the system alters the distribution of energy and curvature in spacetime, effectively changing how objects move without direct mechanical action. This subtle approach is what makes CASIMIR propulsion so unique and potentially revolutionary. Throughout this chapter, one theme stands out. Boundaries are not just passive features, but the very engine block of the AEON-CASIMIR system. Every aspect of propulsion, from thrust to curvature control, depends on how these boundaries are designed and manipulated. This shift in perspective opens up new avenues for research and development in advanced field propulsion. Creating artificial asymmetry in the vacuum is not just a theoretical exercise, it's a practical engineering challenge. The AEON-CASIMIR system achieves this through meticulous design of cavity shapes, materials, and electromagnetic properties. By breaking the natural symmetry of the vacuum, the system unlocks new forms of energy and momentum transfer, paving the way for next-generation propulsion technologies. Zero-point energy is the lowest possible energy that a quantum system can have, and it's present everywhere in the vacuum. The AEON-CASIMIR system shapes this energy by engineering boundaries that direct its flow and intensity. This ability to manipulate zero-point energy gradients is at the heart of the system's propulsion capabilities, allowing for efficient and controlled movement through spacetime. One of the most innovative aspects of the AEON-CASIMIR approach is its ability to couple nanoscale quantum effects to macroscale spacetime curvature. This is achieved through coherent summation and precise boundary engineering, allowing the system to translate tiny quantum forces into large-scale, usable effects. This coupling is what makes the technology both powerful and versatile. Metamaterial boundaries used in AEON-CASIMIR systems are designed with phase-locked reflection coefficients. This means that the reflected electromagnetic waves remain in phase, reinforcing the coherence of the system. Such precise control over phase relationships is essential for maintaining the stability and efficiency of the propulsion core. Directional permeability tensors in the metamaterial boundaries allow the AEON-CASIMIR system to control the flow of magnetic fields with great precision. This anisotropy is key to breaking the standard CASIMIR symmetry and generating directional vacuum stress. By tuning the permeability in different directions, the system can optimize performance for a variety of mission profiles. Negative effective permittivity is a hallmark of the metamaterials used in AEON-CASIMIR cavities. This property allows the boundaries to interact with electromagnetic fields in unconventional ways, further enhancing the system's ability to manipulate vacuum forces. Negative permittivity is a key enabler of the advanced field effects that define this propulsion technology. Piezoelectric lattice deformation is one of the active tuning methods used in AEON-CASIMIR cavities. By applying an electric field, the lattice structure of the metamaterial can be deformed, changing the cavity geometry in real time. This enables dynamic control over the CASIMIR effect, allowing the system to adapt to changing operational requirements. Plasma pressure loading provides another means of tuning the cavity geometry. By adjusting the pressure of plasma within or around the cavities, the system can fine-tune the separation and orientation of the boundaries. This method works in concert with piezoelectric deformation and electromagnetic phase biasing to provide comprehensive control over the system's behavior. Electromagnetic phase biasing is the third pillar of dynamic boundary modulation. By controlling the phase of electromagnetic fields within the cavities, the system can further refine the Casimir effect and maintain coherence across the entire stack. This level of precision is essential for achieving the high performance and stability required for advanced propulsion. Harmonic detuning is a technique used to prevent runaway instabilities in the AEON-CASIMIR system. By ensuring that the natural frequencies of the cavities are slightly offset from each other, the system avoids resonant amplification of unwanted modes. This contributes to the overall stability and safety of the propulsion core. Cavity phase staggering is another stability measure. By intentionally offsetting the phase of each cavity, the system prevents the buildup of large, coherent oscillations that could lead to instability. This technique, combined with plasma damping and harmonic detuning, ensures that the AEON-CASIMIR system remains robust under a wide range of conditions. Plasma-mediated damping is a critical component of the AEON-CASIMIR stability strategy. By using plasma to absorb and dissipate excess energy, the system can dampen unwanted oscillations and maintain control over the vacuum forces. This approach is especially important in high-energy environments where stability is paramount. With all these elements in place, Chapter 5 of the AEON-CASIMIR Dossier stands complete. We've explored how boundary engineering, metamaterials, and advanced quantum effects come together to form the physical engine core of a revolutionary propulsion system. This chapter lays the groundwork for future advancements in field architecture and sets the stage for the next generation of space exploration technologies. As we conclude this chapter, it's clear that the AEON-CASIMIR approach to propulsion is not just about moving through space. It's about reimagining the very nature of motion, energy, and spacetime. By mastering boundary engineering and harnessing the power of metamaterials, we open the door to new realms of possibility. The journey is just beginning, and the future of field propulsion has never looked more promising.